Okay, we're going to go through forces and beams in cables, and you're going to really want to pay attention to the different beam designs here to make your spaghetti bridge. There's an extra credit lab that if you haven't quite got a 50 out of 50 on previous homeworks, or you need to somehow bump that homework grade up, this will be a great opportunity for you to do a lab, get started on your spaghetti bridge, and bump your homework grade up if needed. This will be looking at internal forces, so not the forces over here at the support, but inside of the cable and inside of the beam themselves to see where they will break. So if you take a column or a beam and you cut into it and you look at the different types of loads that is being supported, so this is the beam itself resisting bending and resisting getting torn apart. In 3 dimensions, there are 6 different reactions you're going to worry about. You have the axial force that's coming just along the long dimension of the beam. You also have 2 different shear forces. As well as the axial and shear forces, you also have to worry about bending moments. So all the different ways that this beam could bend in the X, Y, Z. In 2 dimensions, you have just an axial force, a shear force, and a bending. So inside of that beam, there's 3 different reactions to solve for. Okay, so just a couple definition. A beam will be a solid piece of material. You'll have some tension happening at one side of your beam with compression happening at the other side. The thicker your beam is with respect to where that rotational axis is, the stiffer it will be. So you can see that the same beam oriented differently will support loads differently. So this is one thing to kind of keep track of. This is one of the points of why you have an I-beam. The more material you have far away from the axis of rotation that has to be compressed or in tension, the more resistant to bending it will be. Okay, so that's a beam. For cables, the nice thing about cables is they're only in tension. And if you're ever working around cables, be very, very careful around them because there's actually quite a lot of elastic energy that can be stored in these things. So, take a rubber band and break a rubber band and feel that elastic recoil that happens when it breaks. The same thing happens with a steel cable. So if you ever see a cable that looks frayed or is looking rusty, that's a cable that really needs to be replaced, and you don't want to be anywhere near it because when those things break and snap, they will whip around just like a rubber band that breaks. And so they're great to hold up loads, but you have to be very, very careful about the maintenance issues on these guys. Okay, so internal forces. If you have a 2-force member, that is where you're going to have straight tension or straight compression. If I take this beam and I slice it through point C, inside point C, these internal forces are going to be equal and opposite to what was happening at the support. So these straight tension, compression, 2-force members, that's your simplest scenario. You don't have to worry about bending moments in this case. If you have a 3-force member, so forces are applied, or a multi-force member, you have forces at more than just 2 places. That means that when you cut inside of here, you're going to have more than just a straight axial force. So this pole is resisting bending, which means there's an internal moment inside of this. And you can draw a free body diagram of each chunk of this thing, just like you would draw a free body diagram of anything. So you're going to dissect it, take just one piece, and wherever you cut through it, you'll replace that area with a bending moment, an axial force, and a shear force. And you can add everything in the X direction, everything in the Y direction, and the bending moment on this needs to add to 0 just like it does for any objects that you would draw a free body diagram of. If it is a two-force member, but that two-force member is broken, in this case you would have a moment, a shear, and an axial force in here. So the simple case where you have the tension inside is the same as the tension that is pulling at the supports. This only works for a straight two-force member. So just think about right before this fails, is it going to bend before it fails? If it's bending before it fails, there's a bending moment in there that's going to have to be fighting against that material deformation. If it's pulling apart like taffy, that's going to be just a straight axial force. Or if there's some kind of a shearing force happening. So just think about how it breaks, and that will tell you how to write the reactions. The safe way is to always just include axial, shear, and bending force inside of there and slowly go through and see which ones are going to be present inside. Okay, so just a quick note on what is considered positive and what is considered negative with these guys. So let's say we have a beam and we're going to slice into the center of this thing and draw in the reactions internally into this beam. You'll always have equal and opposite forces and moments on each side of that slice. And what they've done is to define positive with your positive moment. So remember, the positive moment is counterclockwise. If you use your right hand rule, or you can think of like unscrewing something, so it's unscrewing out of the board. This is positive moment. And a moment in this direction is always going to be paired with a shear going down, and this is a confusing part. This shear moment combination, both of these are positive. So shear going down is positive versus over here, this would also be positive. So when you're looking at this side of your bending moment diagram, down is actually positive, and here's your positive moment. If this drives you nuts, remember, instead of writing plus or minus next to your answer, you can just draw the direction by putting an arrow next to it, and that's probably going to be more clear to just draw in the direction of your moment by including an arrow and draw in the direction of your shear by adding an arrow in there. Let's go through some example problems. So here we have a frame and we've got a couple of multi-force members. So here we've got 1, 2, 3. We also have, this is 1, 2, 3. So they're all multi-force members, which means we're going to have bending moments, shear, and axial forces inside. Okay, so what we're going to do, determine the internal force in member ACF. So here's ACF at point J. And we're also going to determine BC, this BCD member, what is happening at point K. So see how J and K, these points are inside of the beam itself. Before we get what's happening inside, we'll first have to look at what's happening at the supports, and then once we figure out what happens at the supports, then we can slice inside of this and see what's happening internally. Okay, so this is, the first thing we're going to do is reactions at the connection. So what's happening at F, what's happening at E, and then if we draw a free body diagram of the entire beam, what's happening at C, and then once we know what's happening at all those connections, then we'll take off just a little chunk of it and see what's happening internally. So this will start out just like chapter 6 problems, and there's just one more extra step at the end where we're looking at internal forces. Okay, so after we have externals, we're going to slice it apart at these internal positions, draw a free body diagram of just one little piece of it, and look at what would balance all those forces using the internal forces. So let's start going through here. If we had a roller support at F and a pin support at E. This is a free body diagram of the entire frame. So the only external force for the entire frame would be this 2400 newtons applied at D. And then we have the external forces applied at points E and F. Okay, so how can we solve for EX, EY, and F? Remember, the easiest way to solve these is with a moment equation. The most unknowns are happening over here at point E. So if we take the moment around point E, that is going to be our 2400 acting down times, this is 3.6 meters. So you see that 3.6, 2400, and that's going to be a negative moment. We're going clockwise from that 2400, so that's pushing back into the board. And then the other moment is the force at F, so we come all the way over 4.8 meters to the force at F, and that would create a positive rotation around E. So it's just 2400 versus F, and you solve for F. And then once you have F, F is 1800, here's 2400, so you can see F is not holding up that entire 2400 newtons. So if we look at everything in the Y direction, there's where we get EY. So 600 for EY plus 1800 times F is equal to 2400 newtons, holding it down. And you can see that since that 2400 newtons is kind of closer to the F side, that F is holding up most of that weight. So it's heavier over on this right-hand side where F is than over on the EY side. Last but not least, what's happening in the X direction? I don't see any external forces in the X direction. So that means we don't have to worry about EX. EX ends up just being 0. Okay, so now that we have the external forces, we're going to start drawing free body diagrams of each individual piece of it. Okay, so let's start with B, C, D. How many unknowns do we have on this? This is not a two-force member, so we do not know the direction. So that means we have two unknowns, BX and BY, CX and CY. Two unknowns at each of this, 4 unknowns. So that's more unknowns than we have equations, right? We only have Fx, Fy, and moment. So how can we solve for 4 unknowns? Well, we have more than just this beam to draw a free body diagram, but is there anything you could solve for from this? Let's think through that. Okay, so here's the next piece. If we draw a free body diagram of this piece, again, we have 4 unknowns. Now, the point B here, whether you're looking at one beam or the other beam, these are going to be equal and opposite forces here. So between the two of these, we actually have 6 equations, and we have C, A, and B. We have 6 unknowns. So when you draw the free body diagrams of 2 beams instead of just one, that gives you more equations and ability to solve for more unknowns. The last thing we're going to draw a free body diagram of is this ACF beam over here, and then realize that the forces up at the top at A, whether you're solving for it from this beam or this beam, these are going to be just equal and opposite to one another again. Okay, so for this one, we know our 1800 force over here at F. For this one, we know our force at E. So we can start walking through all of these free body diagrams. So let's start with this horizontal beam here. So what could we do? Remember, starting with moments is usually the best way to start with these problems. So here is, and we could have taken the moment around C or around B. It doesn't really matter at this point. The X component of the force, X does not contribute to the moment around B. See how X is pushing and pulling but not rotating. So for this one, we actually can solve for everything in the Y direction. So you have 2.4 plus 1.2, that gives us 3.6 meters to the 2400 point, so going from B to where the force is applied. And do you see why that would be a negative force from that 2400? We're going clockwise, we're drilling it back into the board, and then CY then is going to have to be going up. So it's 2400 rotating it clockwise versus CY rotating it counterclockwise, and there's one of our Y forces. And if we have 2400, CY is going up with 3600, this is kind of like that teeter-totter arrangement. If you ignore what's happening in the X direction, this would be like the fulcrum of the teeter-totter and someone sitting on one side of it and the other side of it. Okay, so would you expect BY to be larger or smaller than 2400? So here's your BY is only 1200. See, a longer lever arm means a smaller force. So you have, that would be like someone small sitting over here versus someone larger sitting over here on your teeter-totter. And you'll always have those stripes, down, up, down, to balance moments and to balance the forces in the Y direction. So even though we had 4 unknowns and we can't solve for anything in the X direction, so if we write the equation for the X direction, we have 2 unknowns here. We can't solve for anything, but we were at least able to solve for what was happening in the Y directions. Going to our next beam, and remember we have our CY and our BY, so we can use that B force. So if it's pushing down on this beam, that means it has to be pulling up over here. So we have equal and opposite BY forces, and we know this guy. Okay, so for this member, how should we start? Let's start with a moment, and you can take the moment around point A, or taking it around B would have been equally well. So if you take the moment around A, everything in the X direction again, or the Y direction in this case, is pushing and pulling. So BX would be the only thing that would cause rotation, and so BX ends up being 0. Do you see why that would be? So there's nothing to balance that rotational motion from X. So if BX is 0 and that applies over here, that also applies over here. If BX is 0, what's CX? So that means CX is 0 too. So that simplifies things quite a lot. Okay, so we have BX is 0, that means AX is 0, and CX is 0. We don't have anything going on in the X direction for this one. For the Y direction, so we have 600, and then we have 1200 that we solved for. So AY is going to have to be 1800 newtons, and it's going to be coming down. So here's for the members B, C, D, and we've got quite a few of our forces happening already. Okay, so now that we have all of the reactions at the supports and the reactions at all of the pins, we can finally start chopping these beams apart and looking at the forces internal to the beam themselves. So let's start with this point J right here. What we're going to do is take this top little chunk and isolate it. We could either analyze the base of this or the top. The top looks like it's a little less complicated. So let's just look at the top piece here. Okay, so here's just a close-up of the top of this beam, and we need to make sure that all of the forces in the axial direction, the normal direction, and the moment add together for this. So look at the orientation of our coordinate system. We're going to orient our Y direction with the shear force and the X direction in the axial force. Okay, so plugging through the dimensions, you can find what angle that 1800 newtons is with respect to the axial and shear directions. So in the axial directions, that's going to be the cosine theta chunk of it. And the shear direction, that's going to be the sine chunk of it. And we have three unknowns, the axial, shear, and moment. So all three of these reactions are unknown, and we have three equations. So moment, Fx, Fy. Let's start with the moment. Where would be the best place to take the moment around? Well, so J is going to be the best place. This is where all of our unknowns are. And if you take the moment around J, you're going to have 1,800 newtons times 1.2 meters. So we're going over, and that gets us to our 1,800 newtons. See this little distance right here? And this you can get just from dimensions that are given over here. So this is that 1.2 meters that is straight horizontally over. So that's the perpendicular combination. And this little guy right here, that's the internal moment that resists this beam being bent. So inside there at point J, there's the material is resisting being bent, and that's going to be due to how far away that 1,800 Newton force is. So instead of J, if we start walking down this beam and getting farther and farther away from the arm, getting a larger and larger R, that internal moment is going to get larger and larger and larger as we walk down that beam. So don't just solve for one case. Think about what is happening internally at different points. So if you're really close, that's a really short moment arm, and the moment isn't too big. But as we get farther and farther away, this little guy is going to grow proportionally to the distance. Usually beams will break because of the moment, because the moment is never just a force. It's a force times a distance, and that distance, this is always going to be the combination that breaks it. In the x direction, so this is in the axial direction, and we're looking at the cosine theta piece of that 1,800. So there is our axial force. And in the shear direction, remember when the shear is pointed down, we're actually going to call that positive. But we have the 1,800 newtons going up, and to balance that, the shear is going to have to be this 1,800 sine 47 down. So there's our axial force, shear force, and internal bending moment. And that is looking inside of that little beam and those three reactions that are happening internal to it. And this is, again, is that sign convention. So positive moment is unscrewing out of the board. So positive is counterclockwise, and they've just paired that positive moment and negative shear with both. We'll just call this pair positive. So both of them are positive. And here again is another close-up. So we have the axial force, that's the cosine chunk of that 1,800. We have the shear force, see how everything in the shear direction adds to 0. And we have the moment that's created by this distance times the 1,800 force. So there's the three reactions that are happening inside of the beam itself. So just making a free body diagram of this top little piece to find what happens at that point J. Next up, let's see what is happening inside at point K. So this is the same thing. We're going to slice the beam at half, and we can choose to either look at the right half or the left half. Either one will get us what we need. The left half has a little bit less going on. There's only this 1,200 Newton force on here. So what would those internal forces be? Well, there's nothing in the x direction. So in this case, there's no axial load. This force is 0. In the shear direction, it's going to be 1,200 down, 1,200 up. And this is that weird sign convention where the shear going up, we're going to call that negative. And for the moment, so if we take the moment around point K, that's just going to be 1.5 times 1,200. and that little R cross F, to counteract that, this moment arrow is drawn in the opposite direction too. So our moment is going to be negative. So we would be fighting this guy coming down. Let me just draw this in. So around K, our moment is actually going to be going in this direction, right? So we have the 1200 acting one way, and so internally we're going to be in here in the negative direction. So that's that negative moment in here, and that's just like screwing it into the board. So there's the positive versus negative, and these two moments are going to add to 0. Okay, so internal to this one, the moment is our negative 1800, nothing in the axial direction, and then the shear direction, 1200 down, so we have 1200 up, and 1200 up is considered positive. So this guy is actually going up.